Back in 1950, over an ordinary lunch, physicist Enrico Fermi asked a question that astronomers have not been able to shake off since. If intelligent civilizations are even a little bit common, and if technology keeps spreading the way it did during his own lifetime, then the galaxy ought to be full of them by now. Give any civilization just a few thousand years of steady technological development, and its ships and probes and signals should have had time to reach every corner of the Milky Way. So, as Fermi himself put it, where is everybody? You can hardly blame Fermi for thinking that way. He lived through the most rapid burst of technological change humans had ever experienced. He was born into a world with no cars, no airplanes, no radio, and no electric light in most houses. And he lived to see jet planes in the sky, television in the living room, and the atomic bomb. In the middle of the 20th century, it felt entirely reasonable to assume that pace would just keep going. But it didn't. In most fields, progress has noticeably slowed since then, and nowhere is that slowdown clearer than in spaceflight. We went from first reaching orbit to walking on the moon in less than 10 years, and then for more than 50 years we went no further. We did keep sending robotic probes outward. Pioneer and Voyager have both now passed the orbit of Neptune. But robots that cannot make copies of themselves do not answer Fermi's question. They just stretch our reach a little bit farther, one enormously expensive mission at a time. Mathematician John von Neumann took that puzzle and made it even more unsettling with a simple thought experiment. What if a probe did not just fly to another star system, but used the material it found there to build copies of itself, and then sent those copies onward? One probe becomes 10. 10 become 100. It is exponential growth. The same quiet mathematics you see when mold spreads across a piece of bread forgotten in the fridge, only now spreading in 3 dimensions across a whole galaxy at whatever fraction of the speed of light those probes can manage. If that is physically possible at all, then by von Neumann's logic, the galaxy should have been infected with self-replicating machines a very long time ago. And so we're back to the same question. Where is everybody? Just a few years ago, astrophysicist David Kipping at Columbia University decided to actually run the numbers. He built a mathematical model to ask how rare a civilization capable of building self-replicating probes would have to be, and still end up filling an entire galaxy, or, if you follow the logic further, an entire universe within a reasonable amount of cosmic time. And the answer turns out to be surprisingly forgiving. If those self-replicating probes travel at only a tenth of the speed of light, a speed we are already seriously talking about for real spacecraft, using powerful lasers to push light sails and nudge small probes toward the nearest stars, then it would be enough for just one civilization to appear in roughly 1 out of every million galaxies, and within about 1 billion years, every galaxy would be filled. Push that same calculation out across the age of the observable universe, and it gets even stranger. If even a single civilization, anywhere at all, ever figured out how to send probes at close to the true speed of light, that alone, given enough time, would be enough to fill the entire universe with self-replicating technology. There's a strange little wrinkle any model like this has to deal with, and it comes from the universe itself. The universe is expanding, which means a probe travelling at a steady, fixed speed can simply fail to keep up. The gaps between galaxies keep growing, and if it sets out too late or moves too slowly, it will never outrun them. That's precisely why that 1 in a million galaxies threshold matters so much. You need enough separate starting points, scattered widely enough across the universe, that at least a few of them happen to be close enough to their neighbours to make the jump before cosmic expansion pulls everything permanently out of reach. Once you allow for probes that travel much closer to the speed of light, that constraint largely falls away, and the paradox turns into something much closer to a genuine cosmological argument. Either advanced civilizations essentially essentially never arise at all, or something makes them deeply reluctant, or simply unable, to ever begin replicating outward. Because if even one had done so at any point over the past several billion years, we probably wouldn't be sitting here having this conversation. There would already be a probe sitting right here on the table in front of us. Which leads to a rather more unsettling thought. Perhaps one already is here, and we just haven't found it yet. You see, if a self-replicating probe is optimized to travel fast, it is optimized to be small. It's the same logic behind the real proposals today for gram-scale interstellar probes. A small, ancient, silent object like that could be parked in orbit around the Moon, drifting quietly somewhere between Earth and Mars, or sitting perfectly still on the surface of some asteroid we've never had any real reason to visit up close. And we would have no way of knowing. Even the worlds in our own solar system that we tell ourselves we've mapped in exhaustive detail, the Moon, Mars and their neighbours, photographed for decades, and in the case of the Moon, literally walked upon, still have enormous stretches of surface that have never been closely examined, where a small object could sit undisturbed for 1 billion years, just waiting. If we ever did find one, even dead or dormant, the payoff would be almost beyond imagining. A fragment of memory that might contain the accumulated history and technology of an entire alien civilization, or several at once. And humanity is already having that same conversation about itself, only in reverse. There's a long-standing idea to build a compact archive holding everything on the internet, every language of Wikipedia, every photograph and social feed, just in case something out there finds one of ours first and wants to know what we were like. Not every hunt for ancient technology has to look out toward the stars. There's a much more grounded, practical question, much closer to home, in a place out in the outer solar system that has quietly become one of the most talked about destinations in all of planetary science. Titan, Saturn's largest moon. Titan is, in almost every practical sense, a richer world than the Moon. Water on the lunar surface is scarce and hard to reach, locked away mostly in permanently shadowed craters near the South Pole. On Titan, water ice is essentially everywhere throughout the crust, and on top of that, it has in abundance something the Moon has none of at all: hydrocarbons. Titan has lakes and seas of liquid methane and ethane, real methane rivers, even methane rain, a complete working weather cycle, just built out of natural gas instead of water. And that's not just a curiosity. That's rocket fuel and stove fuel sitting there on the surface in liquid form, ready to use. Where Titan might actually prove priceless, though, is nitrogen. And that brings us to a small detail that people who like to sketch out plans for terraforming Mars have a habit of glossing over. The usual story for Mars goes like this: make the atmosphere thicker and the rest will take care of itself. It will get warmer, the pressure will become breathable, you'll get a world you can live in. But Earth's atmosphere is not mostly oxygen. About 80% of the air in the room where you're sitting right now is nitrogen. We don't breathe it in for energy, but we still need it there, because trying to breathe pure oxygen at normal pressure is genuinely dangerous. It's chemically restless, and in it, just about anything would catch fire far too easily. On Mars, you could get oxygen without too much trouble by splitting water into hydrogen and oxygen. What no one really has a convincing answer for is where Mars would find the enormous amounts of nitrogen a proper Earth-like atmosphere would require. Titan, on the other hand, has an atmosphere that is almost 95% nitrogen, in its proportions closer to the air we breathe than anywhere else in the solar system. Add just a little oxygen cracked from its water ice, and you suddenly have something remarkably close to breathable air, sitting under a gravity field only about 1/7 as strong as Earth's, and beneath an atmosphere so thick it completely shields the surface from cosmic radiation, the way ours does on Earth, and the way the thin veil on Mars does not. There is a serious catch here though, and curiously enough it isn't the cold. Titan's surface today sits at around -180 degrees Celsius. And a problem like that, at least in principle, can be dealt with locally, with the kind of compact nuclear reactors that are already being worked on for the Moon and for future deep space missions. The real catch is getting anything back off the surface again. Titan is one of the two largest moons in the solar system, and its escape velocity is about the same as the Moon's, except the Moon has no atmosphere to push through, while Titan's atmosphere is even thicker than our own here on Earth. Even launching a rocket from Earth means burning most of your fuel just to punch through the air as quickly as you can. Trying to launch from Titan would be considerably harder still. Getting down there is the easy part. That dense air is so thick, a parachute alone can lower a spacecraft gently to the ground. Getting back up is the problem, which means that whatever resources we might one day extract on Titan will, in all likelihood, stay on Titan for the foreseeable future, rather than being shipped off to anywhere else. And perhaps that isn't a flaw in the design, so much as a quiet hint about what Titan is actually for. In roughly 5 billion years, the Sun will swell into a red giant, and Earth and the Moon and Mars will all be scorched by the Sun and stripped of whatever atmosphere they have left. If humanity, or whatever comes after us, is still around then and needs somewhere else to go, Titan is one of the very few realistic candidates we already have out there in the outer solar system, with a solid surface area roughly comparable to all of Earth's continents put together, an atmosphere that is already mostly the right gas, a gentle gravity that a person could live with, and more water and hydrocarbon fuel than anyone could ever reasonably use. It is not really a supply depot for the rest of the solar system. It may be something else entirely, a lifeboat for the species, only one built on a timescale far, far beyond anything sitting on a mission planner's desk today. Closer to home, and a good deal sooner, NASA has finally released the formal technical requirements for its next lunar rover. And if you read them closely, you can see just how different this next chapter on the Moon is going to be from the last one. The first lunar rovers, 3 of them flown on Apollo 15, 16 and 17, did a wonderful job for what they were. Think of them as clever folding electric buggies that let the astronauts cover tens of kilometers instead of just a few hundred meters on foot. And that completely changed how much lunar geology those expeditions could bring home. But those stays were brief, and they were planned quite deliberately for lunar morning, when the surface temperature hovers around a rather pleasant 0 degrees Celsius. A full lunar day is a different story altogether, swinging from about plus 120 degrees at noon to around minus 170 at night. And the permanently shadowed craters near the South Pole, the very places every moon program is now aiming for because of the water ice hidden there, can drop to minus 240 degrees or so, so cold that an ordinary battery simply gives up. The new rover has to endure that whole range. It has to be able to work with no one on board at all, either on its own or driven remotely from Earth, since long stays on the surface are still limited by radiation. And it has to keep going for years, not just for a few days. The contract has gone to a private company called Lunar Outpost, with the first field trial at the lunar South Pole planned for November of 2027. It'll be a 2-astronaut rover fitted with a robotic arm, a small cargo bed, and even a trailer hitch for hauling larger equipment. And it will ride on the same kind of flexible metal mesh wheels the old Apollo buggies used, rather than anything pneumatic. Its top speed is limited to about 15 kilometers per hour, which on that terrain is more than enough. But while the original rovers could manage only a few tens of kilometers on a single battery charge, this one is meant to top itself up whenever there is sunlight, and to cover up to 1,000 kilometers over the course of its working life. And there's one more story worth hearing, and it comes from much, much farther out. Not long ago, astronomers pointed the James Webb Space Telescope through the thick veil of dust that has always hidden a dense star cluster near the very heart of our galaxy, a cluster called Terzan 5. And what they saw inside was not a single family of stars, but several at once. Some were made of almost pure hydrogen and helium, as old as the galaxy itself, born in the earliest days of its formation. Others were clearly built from material enriched by earlier generations of supernovae, and some of them are remarkably young by galactic standards. Now, that kind of layered history simply shouldn't happen in an ordinary cluster. The only way it really makes sense is if Terzan 5 was once something else entirely, the dense, compact core of its own small galaxy, one that has spent billions of years being slowly swallowed by the Milky Way. After all, that is how large galaxies grow, largely by devouring smaller ones. Even today, our own galaxy has some 500 to 600 smaller companions orbiting around it, and the largest of them, the Magellanic Clouds, we can already see being pulled apart and absorbed. But there has always been a mechanical puzzle here. When a small galaxy is torn apart by our galaxy's gravity, why would its densest core sink all the way down to the very center, instead of just scattering somewhere out on the edge? The mathematics that answers this, a slow, steady braking effect known as dynamical friction, where a massive object moving through a sea of lighter ones gradually loses its orbital energy and spirals inward, was actually worked out a long time ago, back in 1975. 2 Soviet astronomy students modelled the problem on one of the slowest computers their institute had at the time, and in one of the very first calculations of its kind, they showed that star clusters really should sink toward the centre of a galaxy in just this way over billions of years. And Webb's new look at Terzan 5 is, in a sense, that old prediction finally coming into view. A fossil hiding in plain sight near the middle of our own galaxy, the remnant core of a small galaxy that fell in long ago and never quite dissolved away.